Hello, and welcome to today's webinar from Expedera entitled Optimal Neural Network Acceleration via a Packet-Based Architecture. My name is Paul Karazuba, and I'm the Vice President of Marketing at Expedera. Today's webinar will take you through Expedera's unique packet-based architecture for AI acceleration, including a background on the approach, how it works, and the value it brings to our customers. So let's go ahead and get started. So a very brief introduction to Expedera for those who may not know us yet. We're a Silicon Valley startup revolutionizing the AI inference market by applying networking principles known as packets. And we're going to detail this a lot more in our talk today, including how we provide unsurpassed performance. Although we only exited stealth mode in 2021, we're already shipping in a leading consumer device and are silicon proven in a number of leading edge fab nodes. Our diverse team of artificial intelligence, SoC, and IP experts come from a wide-ranging background at leading silicon and IP companies. Most recently, we exited stealth with a series of announcements, including the first public unveiling of our novel packet-based AI architecture and the closure of our Series A funding. First, a very high-level introduction in our AI product. In our quest to build a more efficient AI accelerator, we took a look at what was the state of the art. We analyzed the different architectural approaches for neural network processing used by leading companies and discovered that the one fundamental limitation in advancing the performance of those AI accelerators is the work units that the neural networks are broken down into. And I'm going to explain a whole lot more about this. To address this deficiency, we asked ourselves how we should define those work units, or perhaps better said, how we should redefine those work units, and brought to market the approach of packets. With packets, we're able to simplify the software stack and increase the performance of our DLA or deep learning accelerator. The packet architecture allows us to right-size our DLA early in the architecture phase, ensuring that our customers receive an optimum AI engine for their needs. And packets provide for seamless deployment in applications which range from persistent streaming applications to multiple jobs in high TOPS environment. Now, I know I've introduced a lot here. Let's go a lot deeper. We'll first examine AI workload performance. Simply stated, we have a multidimensional problem. Different measures like throughput, accuracy, latency, utilization all affect performance. But unfortunately, these measures often don't play along well with each other. Let's use a couple of examples. First, let's use throughput. A faster engine is generally perceived to be better. But to increase throughput, you increase batching so that the weight load is amortized. And as you do that, you add latency. Adding latency may not be acceptable in a lot of applications. Now, another example. Let's say you want to enable higher precision quantization to improve the accuracy of your networks. Now, that's great, but the unintended effects of this are higher power consumption as well as lesser utilization. Again, perhaps not acceptable. What really defines acceptable really varies dramatically from design to design or market to market or customer to customer. And if you take time to survey existing performance benchmarks, you'll realize that for AI inference, the utilization of most SoCs stalls anywhere from 20 to 40%. And this is true for even well-known benchmarks like ResNet. This has led to existing AI solutions being dependent on complex compilers, and unfortunately, these compilers only yield incremental benefits. Because of the 20 to 40% utilization, chip architects are forced to over-design SoCs in terms of processing power and memory to meet application demands. And inevitably, when applications hit their power or processing budgets, they have to be retrained or scaled back, neither of which is ideal for deployment. So let's step back and think about this for a second. AI processors typically only achieve at best 40% utilization, and chip designers should be okay with that. Quite literally, their AI processor is sitting, idling, waiting for something to do 60% or more of the time. I mean, just think of the wasted cycles and the wasted power that entails. There has to be a better solution for this. Let's jump to compilation. Compilation, of course, as you know, is the process of taking the entire neural network and breaking it down into smaller work units. And there are challenges here. Let's go through three. First, compilers need to understand layer connectivity. That understanding must not be just local, but global. They need a holistic view of how each layer is connected across the entire neural network. And this is important as it defines where intermediate activations are generated and also where they're consumed. A second problem for compilers is intra-layer dependency. Activations and weights are best thought of as four-dimensional tensors, and we need to consider how they correlate with each other for data reuse and relation to where the results are. These depend on the properties of the neural network. For a convolution layer specifically, kernel size, stride, and padding would impact how different pixels of activation relate to each other. And the third challenge is hardware mapping. Compilers must understand the workload and map it to hardware, depending on dense compute or vector compute. All the while, they must manage the shared resources of on-chip memory and system fabric and system DDR access in terms of bandwidth. Without any assistance from the hardware, all of this responsibility lands in the compiler, which must enable it through fine-grained synchronization. We found that current architectures really are limited by work granularity, and we'll use two examples to demonstrate this. The first, on the left, the CPU-centric approach, which uses instruction as a work unit, and on the right, the interpreter-centric approach, which uses a neural network layer as a work unit. Let's compare and contrast. The CPU-centric approach is known, having been with us since the beginning of computing. It's well understood, it's optimizable, it's flexible, and it allows multiple applications to coexist quite seamlessly. But CPUs don't have a notion of scheduling built in. This means any work must rely solely on synchronization primitives. The memory hierarchy in the system are cache-based, which means they're not deterministic, and even a simple change like where a tensor is located can completely change the memory access pattern. And finally, because a layer needs to be broken up into multiple compute blocks and then gathered back, they are limited in terms of power efficiency. Now, when we look at the interpreter-centric approach on the right, they're simple. And due to their simplicity, they can do just-in-time compilation, but they're limited. They can only perform layer reordering optimization, they have limited scalability, and require large amounts of expensive on-chip memory. Neither of these approaches is ideal and have significant drawbacks. In examining these, we've determined that we need an abstraction for a work unit which is somewhere between the instruction and a layer. And this is where and how we define a packet. Packets. Packets are an aggregate of work with a notion of dependencies and deterministic execution. For computation, a packet can be defined as a continuous fragment of a neural network layer, which includes the entire context of execution. What layer type it is, what attributes it has, padding, stride, kernel size, what priority it has, high or low, as well as what precision it can be executed on. So the first step is to divide the neural network layer into packets. The example you see is the second convolution being broken down into 4 packets and the max pool broken down into 3 packets. Once we have the packets, the second step is actually reordering them. The ordering of the packets, which is done by our patented reordering algorithms, is based on our customers' objectives, which can be minimizing latency, reducing bandwidth, increasing throughput, others, or any mix of the above. At the reordering step, what we then get is an optimized packet stream, and we've designed our DLA to execute this packet stream natively. Within this diagram, you can see that the hardware sequencers are responsible for taking the packet streams and distributing this work on top of our DLA engine, while our resource manager handles memory and bandwidth. So how does a packet-based DLA benefit system designers? First, let's examine actual packet execution. I've talked about how we construct packets as work aggregates. In doing so, we've created a work unit which can be fully utilized on our hardware. This results in very high throughput and gives us a 70 to 90% utilization metric compared to the 20 to 40% benchmark of existing methods that I talked about earlier. And to note, we don't require changes to our customers' pre-existing neural networks to achieve this, and I can't underscore the importance of this. We don't require retraining and we don't require modifications to our customers' neural networks to achieve our 70 to 90% utilization. Scalability is also an advantage here. Packets are automatically distributed within the DLA amongst available resources. And I haven't talked much about scalability, but let's just say the Expedera DLA can be scaled from under 1 TOPS to 128 TOPS, trillions of operations per second, which allows Expedera to address applications from the most compute-light edge nodes all the way to high TOPS self-driving and data center use cases. And our core scales without affecting memory footprint and without negatively affecting utilization. The scalability ensures the Goldilocks AI engine for our customers. Not too big, not too small. Now, power. Power is obviously a concern as well in any chip-based application. Our packets are sequenced for low power at the cycle level, enabling power-efficient implementations of our AI engine. Let's turn the attention to scheduling. As each packet execution is deterministic, we can determine the best way to schedule the entire neural network to achieve high utilization and, in turn, low latency. This is done by effectively parallelizing compute and data transfer on independent resources of the DLA. Our DLA also supports multi-tenant, or in other words, multi-job deployments, with no overhead to runtime power or complexity of the deployed solution. Each tenant can have its own priority, and based on these, shared memory and bandwidth is allocated to maximize multi-tenant utilization. So let's note that packets have a deterministic nature. We have a complete notion of the execution cycle as well as an understanding of memory and bandwidth requirements that the packet will consume. With this visibility, we can quickly model the customer's entire neural network execution using our estimator tool. This tool accounts for input traffic as well as the neural network with representative data set and a representative model of the SoC architecture, and then traces out the entire neural network execution. So let's cite some real-world examples on how our packet-based approach can save memory and bandwidth. For the example you're seeing here on the screen, we use a YOLO version 3 with an input image of 608 by 608 with a batch size of 2. This has 63 million total weights with 235 million total activations, which executes 280 billion operations overall. Okay, the graph on the right compares the layer-based approach versus Expedera's packet-based approach. And to be clear, to make sure we're not playing games, both approaches are optimized to utilize the minimum amount of memory and bandwidth that is required. What you can see is that the layer-based approach requires 5 times more external transfers than our packet-based approach. And as we all know, the more transfers, the lower the throughput and the higher the power consumption, meaning Expedera can enable higher throughput and lower system power versus other architectures, while reducing system BOM cost via lowering the external memory bandwidth requirements. In terms of utilization, this required bandwidth is spread out over the execution of the entire neural network, which means the utilization that we talked about, 70 to 90%, can be sustained throughout, and we can tolerate latency variations that we see from external fabric or from DDR controllers. So we know that each application is different, and we know that SoCs developers most often have to account for a variety of use cases for a number of markets, and frankly, including ones those designers might not even be aware of as the usage of AI evolves. And these applications may run in parallel and have to coexist. Other AI approaches struggle to solve this. As each AI application is optimized in isolation, the only way for hardware to guarantee performance is by physically partitioning the hardware. But because packet stream execution is deterministic, execution cycles and resource utilizations are known in advance. Using this info, work-conserving scheduling policies can be used to optimize performance and job priorities, making sure that system utilization always stays high. In Expedera's packet-based model, shared resources are optimally used without the need for physical partitioning of bandwidth and of memory. Let's talk software. We've enabled this approach, our DLA, through our comprehensive TVM-based software platform. This platform allows us to interface with existing deep learning frameworks like PyTorch, TensorFlow, Onyx, and others. It also defines a standard interface between the DLA and other SoC blocks, as we know that our DLA is not going to stand alone in a system. Using the same interface, the entire runtime of the neural network is brought under Expedera's umbrella, with important features being mixed precision quantization, custom layer support, and multiple job APIs allowing multi-tenant deployment. And to note, customers have visibility in this from the architecture phase, where they select the right DLA configuration, to the development phase, where the right power, latency, and FPS decisions can be made according to our customer system goals. So how does this actually perform in terms of power, performance, and area? Let's take a step back. I want to address some common ways AI engine capabilities may be listed and what I believe you should look for when examining true performance and deployability of an AI engine. System designers generally make decisions on processors on three main factors: performance, power, and area, or PPA. And you're going to hear me talk a lot about this right here. We talked about TOPS earlier, trillions of operations per second. This spec is a measure of how fast an AI engine can theoretically process information, but it doesn't actually include utilization metrics. For this reason, it can't be considered a true benchmark of an engine's capabilities. The ability to process doesn't mean you actually process in actuality. For this, we need to go to effective TOPS. Effective TOPS factors in utilization. As an example, let's say someone talks about a 20 TOPS processor. While 20 TOPS may be the theoretical maximum performance, that number doesn't factor in, let's call it a 30% average utilization. In reality, the effective performance of this example is 6 TOPS. The 20 TOPS times the 30% utilization. Effective TOPS may be a good measure, a good benchmark of engine performance, the first P in the PPA. A step further, let's also examine the power consumption requirements of that AI engine using a TOPS per watt specification. This specification may be a real-world benchmark for deployability, meaning system designers are always going to have power and performance, the first two Ps, as a requirement in the AI system. Meeting just one of those, power or performance, often isn't a path to success. TOPS per watt, as it measures the performance per 1 watt of power consumption, could be a good metric. This spec obviously covers, as I said, both the first two Ps in PPA. We also need to look at how the silicon area is required for the AI engine, which is where we would employ a TOPS per millimeter squared specification. Obviously, the less area required is better from a cost and deployment perspective. So if you look at TOPS per millimeter and TOPS per watt, you can cover all aspects of PPA. Now, finally, I should note, when comparing two AI engines' TOPS per watt and TOPS per millimeter numbers, you have a number of things that are factored in here, one of which is the foundry process node that the AI engine is built on. Obviously, as chip designers know, as you switch foundries and you switch processes, power consumption and area obviously will scale with your process size. So that needs to be considered. And for comparison's sake, on the next slide, be assured that we are comparing the same process node, the same foundry in our analysis. So let's look at how the Expedera IP performs versus competitive. And this, of course, is third-party data. Start with that. Let's look at the left at TOPS per watt. Expedera's Origin AI DLA can operate at 18 TOPS per watt, easily besting competition. And I want to be clear. This is silicon measured in TSMC 7 nanometer at a 1 gigahertz clock, running common workloads like ResNet. The numbers that we're showing here are not coming from us. They are third-party reported, and you can read more of this on our website. But to be clear, we're not inventing these numbers. We are not simulating these numbers. This is actual silicon performance measured by third parties. Let's also look to the right at TOPS per millimeter squared. What we're seeing here is that Expedera provides 2 times the processing power in the same die area, or a 50% reduction in die size requirements with identical processing versus competition. Okay, so let's wrap up this webinar and I'll leave you with a few parting thoughts. Expedera's packet-based artificial intelligence DLA leads the industry with 18 TOPS per watt and a 70 to 90% utilization, and again, silicon measured and third-party reported. This ensures greater processing efficiencies with lower power consumption. Our approach eliminates complex compilers, allowing our customers to use their existing trained models with no modification, reducing their time to market and extending their time in market. Our unique hardware approach is configurable, predictable, and scalable, allowing our IP to be configured to our customers' unique needs. This ensures that our IP is matched to customers' unique power, performance, and area requirements. And finally, we're quite deployable. We're proven in several advanced fab nodes, we offer standard design and evaluation tools, and we stand ready to answer your questions. So thank you very much for joining us on this very brief introduction to Expedera's DLA and our packet-based approach. If you have questions, you can visit our website at www.expedera.com. You can shoot us a message at info@expedera.com or meet us at any one of our social feeds on LinkedIn, Twitter, or Facebook. Thank you very much and have a great day.